our goal for today is sort of a nice blend of exponential growth and exponential decay. So I wanted to talk to you a little bit about the 7-1 notes that we did not quite get to on Friday, mainly because the copy center didn't copy the packet correctly, so I had to photocopy the little, sorry Danielle, the last couple of bits of notes there. So you grabbed a note sheet when you walked in, and it kind of starts with the word translations at the top. It's actually page 3 of your note packet, so you grabbed that when you walked in. I'd like you to just go ahead and draw your attention to that. Today we translate exponential growth and decay curves, so we're going to translate both. You might recall that to graph a function of the form y equals a times b to the x, like you did on last night's assignment, you basically just plot the y-intercept, maybe 1 or 2 other points, draw on your asymptote, which is that x-axis, and just connect your dots. So you had 3 of those or 4 of those last night to go ahead and do. But today we're going to go ahead and throw h and k into the mix. So now we're going to take x minus h and make that our exponent, and then we start to add on k. You're going to start, of course, just by graphing the parent function, y equals a times b to the x. And then you might recall from, previous lessons that h tells you right, left, and k tells you move it up, down. And I went through this with my period 1 class earlier today. Remember, if it's x minus h, it actually moves to the right. But if it's x plus h, it moves to the left. If it's plus k, that graph moves up. And if it's minus k, it moves down. So the first thing you're going to go ahead and do is identify the transformations that you see in your equation. So in part A here, and we'll do this one together, part B you're going to do on your own. It says graph the equation y equals 2 times 3 raised to the x minus 2 power, and then take away 2. You start by identifying the transformations that you're going to need to carry out. So you'll see I highlighted here this x minus 2. That means that this graph is going to move to the right 2 units. And then the minus k value at the very end moves that this graph is ultimately going to move down 2 units. And then you'll see I grabbed a different color marker, and I picked out the parent function and wrote it right underneath that equation. The parent function, sans any transformation, is going to be y equals 2 times 3 raised to the power of x. So I want you to go ahead, think back to how you did these last night. I want you to graph this equation for me. Y equals 2 times 3 to the x. So you're going to start by graphing that. Did it? So when I drew in my dashed graph, it was blue, and you see it kind of hanging out in there. I guess I can just give you the full reveal now. So yeah, this graph basically started at a y-intercept of 2, and then I just, plugged in -1 and 1 just to get a couple of other points for my graph. And then I did notice that, this graph doesn't move up or down at all, and I really can't get 0 out of that blue function right there. It doesn't matter what I plug in for x. I'm not going to get 0 back out as a y value. So you get that asymptote at y equals 0 initially. Then I took all of the information in blue and I moved it. That was to actually get the graph of the translation of this function. And you might recall that at the very beginning of the problem we talked about, oh, well, if it's x minus 2, that's going to move the graph to the right 2 spaces. And then the minus 2 at the tail end is going to move all the points down 2 spaces. So I took every point and I moved it to the right 2 spaces and down 2 spaces, including the asymptote. The asymptote also has to move. So if it started at y equals 0 and I move it down 2 spaces, my new asymptote is at y equals -2. I can't possibly get -2 out of this function. That ultimately impacts the range. Domain doesn't really change. You could still plug any number in for x. However, you're not going to get just any number out for y. You can't possibly go below -2. So though the domain is -infinity to +infinity, my range values only start just above -2, and those head towards +infinity because this is a growth function. Are there questions about that? Okay, so now you get to try a whole one. Part B, that is all yours. For part B, this is essentially what I would see on your homework tonight. You do have a couple of these to do. If you looked at your 7-2 practice worksheet, you do have a couple of these to go ahead and take care of. They're going to be decay, though, just to give you a heads up on that. Your B values are going to be between 0 and 1. So the first thing I see is a dashed graph for just y equals 2 times 4 to the x. So you have a y-intercepted 2, and then you could plug in 1 and -1 to kind of get, a couple of other real simple points. And then based on this, +1 that's here, I know that I had to move the graph to the left 1 unit, and then this -3 here said that I had to move the graph down 3 units. So I did that. When I move the graph down 3 units, notice what's appearing today that didn't appear on last night's assignment. You do have to draw in that asymptote for me. We didn't have to draw it last night. Who could tell me why? Do you know why? Yeah, it's just the axis, right? It was the x-axis. So you could try to draw a dashed line on that, but that's a big dark line. It might not even, kind of like show up for you. So I didn't make you worry too much about it. But for today, my concern in you not drawing it is that I would see people, swinging well below that line, and that's just not accurate. You can't go below -3, so you do have to set up that boundary for yourself. Make sure that you include your asymptotes on your assignment for tonight. It's, not quite complete if you forget those asymptotes, so that's important. Notice that the moving of this asymptote did ultimately affect our range. Our graph can only now go from -3 up. Not from 0 up, so it is a little bit different because we moved the graph down 3 spaces. A little trick, if you look at this last number on the end of the problem for today, it's going to be your asymptote right there. So, if you're like lost as to what it is, that is your asymptote when you move it down. So a little help there, a little trick for you. Okay, so then you had some word problems to do, and I made you look up a formula on page 481 last night. Looks like you guys did a really nice job with it so far. So you did have to look to page 481, but I did want to, walk you through a couple. The formula that I see you folks doing a really nice job with was this guy here. You have an amount in an account. The initial amount is called P for principal. It's spelled the same way as the principal, like Mr. Crater. It's spelled the same way, like your pal. But that's just an initial amount in an account. That's your P value there. And then to get your growth factor, the number that you actually add to 1 isn't just R, like it was with the buffalo problem. We actually have to take R and divide it by N, and N is actually your number of compoundings in a year. So we take our R divided by N, add it to 1, and then you got to raise your exponent to the NT power. So it's going to be your number of compoundings times time as your exponent there. So as I walk around, it looks like you folks had a pretty good handle on the formula. I did want to do maybe 1 or 2 with you because I see some of you set the formula up but then didn't evaluate it. So this will hopefully squash that for you. So what you'll see here is a little word problem. And an example 4, it says you deposit $2,900, lucky you, into an account that pays 3.5% annual interest. Bless you. So right now, they're just coming right out in the problem. They're telling me the initial amount in the account. In other words, they're telling me what my principal is. This is at the bottom of the note sheet you grabbed when you walked in, I think. Oh, no, I'm sorry. It's right below the buffalo problem. This is in your packet. Page 4, yeah. That's going to bug me, this whole chapter. So you deposited $2,900 in the account. That is your principal. And in this case, the interest rate is 3.5%. So this is going to give us our R value. Remember, you have to convert it to a decimal. So this is 0.035 as our rate. Move that decimal point 2 spaces to the left when you go from a percent to a decimal. And then they say here, your interest is compounded monthly. And we're supposed to find the balance in the account monthly, daily, annually. All of those words give you input into your number of compoundings. If they compound interest monthly, and there are 12 months in a year, that means our number of compoundings is 12. So N is 12 in this problem. And you're just supposed to find the amount of money in the account. So if you look, you have everything you need. You have your P, you have your R, you have your N, and you do have your T, They tell you they want to know how much money is left after 1 year. So you basically plug it in. Where I saw a couple mistakes was with the order of operations. I usually do this in baby steps on my calculator. So if I were going to my calculator right now, I follow the order of operations. So I would do please excuse my dear Aunt Sally. And in those parentheses, I have to take a little bit of time to calculate my growth factor. So there's my rate. Ultimately, I have to add that number to 1. And then that number becomes my growth factor for this problem. After you do the parentheses, you should do the exponent. So the number of compoundings times time. So this number gets raised to the 12 times 1 power, which is 12. And then you multiply that number times the initial amount in the account. Ultimately, I get $3,003.14 in this particular bank account. So there's how I set it up. Threw it in my calculator using the order of operations, and I got $3,003.14. Any questions about that? Looks like most of you did a pretty nice job once you found the formula for yourself. Why don't you try part B? We'll make sure you're okay with it. That looked really good. Okay, so this is your setup for part B. You have 2,900 times 1 plus 0.035 divided by 1, all raised to the 1 times 1 power. If I remember correctly, bless you, oh my goodness, I think I got around $3,001. I can't remember the odd change. What'd you get, Will? 50 cents? So, what do you think? Which situation would you rather have? Notice you're leaving the same amount of money in the bank account for a year. Would you rather have monthly compounding interest or annual compounding interest? Yeah, it's marginal for this problem, but yeah, monthly, right? It's my hope that you start to notice that the more you compound, the more money there is. That'll be important for tomorrow's lesson because we talk about continuously compounding your interest. Okay, there are questions about that? Looks pretty good. All right, there is one last problem there, but I was going to save it as a conclusion problem. Example 5, we are going to come back and fill that in. It's basically the same that we just did. You look like you did a pretty good job with it, but we're going to have you come back and fill in that last example. We're going to go ahead and talk about exponential decay right now. So 7.2. You have a little bit of vocabulary there to start off the lesson. The goal for this lesson is to basically do the exact same thing we did with 7.1, exponential growth, but this time our b values are going to be between 0 and 1. So we graph. We translate the graphs. We use the graphs to solve some word problems. Those are the 3 things we did with exponential growth. Those are the 3 things we're going to do with exponential decay. So we're going to graph, translate the graphs, and use those graphs to solve some word problems. Just again, we're going to have a parent function. These functions that we graph today are going to look a lot like our graphs from our M&M activity. You might recall that the 0, a value is still your y-intercept, so that still applies. What you're going to notice, though, is that as you plug in values that are positive, ultimately your outputs are going to get smaller and smaller and smaller and smaller. So small they approach 0. They don't quite get there. So the asymptote is still the x-axis. It's still y equals 0. And I gave the example in my period 1 class. Like today, you might think about y equals 1/2 raised to the x power as a little bit of an example. So if you're looking at y equals 1/2 to the x power and you're thinking about possible values of x, you can really put in anything you want. There's no real restrictions on, rules that we have to follow for x. You could plug in a negative, you could plug in a decimal, you could plug in pi, really whatever you want. This leads us to come to understand that the domain takes us from negative infinity to positive infinity. However, it doesn't matter what you plug in for x, But as far as what you actually end up getting back out for y, you really aren't ever going to get anything that's negative or even below 0. So this ultimately affects our range. The range of our exponential decay parent functions are just going to go still from 0 to positive infinity. Doesn't matter what you plug in for that exponent, you're not going to get a 0 or a negative number back out. True story. So with that, I had my other class take a couple of minutes, and I made them do these. And I'll do the same with you folks. I want you to just take a minute and graph these two functions. So y equals negative 2 times 3/4 raised to the x power. And then for part B, it's y equals 2 times 1/4 to the x power. Following the same rules that you did on last night's assignment. This time you're going to notice that they face in a different direction. So I'll let you do that. I have to talk to a couple youngsters here for a second. As I walk around, you guys did an awesome job with this. I even threw in a little reflection there and didn't seem to daunt you guys too much. Notice that you still do get this asymptote right along your x-axis again. It's not really such a big deal if there's no translation if you don't have the asymptote down, because I think we all understand that you can't get 0 back out. When it does become a bigger deal is when you translate the graph, because you still can't go above or below certain values when you move the graph up or down. So the asymptotes become big in the next page, and I think you have the next page. I think you had to grab it when you walked in. It was like you had 4 handouts today when you walked in. 2 of them were note sheets. So right now you're flipping to the second page of the 7-2 notes. The top starts with example 2. And this is your chance to get a little bit of practice with translations. So once again, what we're going to go ahead and do is we'll walk through that first one together again. And you'll see that the first thing I always do is I look at my equation and I'm like, oh, you know, what way am I supposed to translate this? And it says x minus 1 as the exponent. See that minus 1 right there? That means I'm going to move this graph to the right 1 space. And then the plus k value at the very end there, that means I move the graph up 1 space. But ultimately, I'm responsible for initially graphing y equals 2 times 3/5 to the x. So I get my y-intercept at 2. And you'll see that my red function there is the parent function. I started graphing y equals 2 times 3/5 to the x. So you'll see there that I had my y-intercept initially at 2. And then I picked values like 1 and negative 1. And I plugged those in just to get a couple of dots. Then I drew in my dashed line, much like you just did 2 seconds ago. Then I had to take all of this information and move it. I had to move it to the right 1 space and up 1 space. So that's what I did. You'll see I started mainly with my y-intercept. I moved that particular smiley face to the right 1 space and then up 1 space. And I plugged in values of 1 and negative 1. For instance, when I plugged in negative 1, initially, you know, I had 2 times 5/3, so 10/3. So a little bit above 3, you know. And then I moved that dot to the right 1 and up 1. When I moved all of those dots to the right 1 and up 1, I also end up moving that asymptote up 1 unit. So you see I have a new blue dashed line there. Again, that number on the very end of your problem, same as in the first section of notes, that number on the end is also going to give you your horizontal asymptote. So that's kind of nice. And then ultimately that horizontal asymptote does give us some sort of information about our range. This graph can only go from 1 up. Well, not even including 1. So it's really, really close to 1, but doesn't quite touch it. Are there questions about that one? example 2, part B, I was going to have you take care of, but I kind of wanted to look at a depreciation problem with you before you left me today. So we're going to round out our lesson today with a little bit of exponential decay. And you'll notice that this formula is almost identical to the formula for exponential growth, but do you see the difference? There's a minus sign in the parentheses. This is because you have to have a decay factor, not a growth factor. So the major difference is that minus sign in there. You're going to take your rate and subtract it from 1. Lots of things depreciate, much to your dismay. A little later on in life, you buy a car. Second you drive it off the parking lot, loses like, I've heard ridiculous statistics as far as that's concerned, like 1/3 of its retail value. It's kind of a bummer. What's up, Calvin? Decrease, percent rate decrease as a decimal. Yeah, A is still your initial amount that the object was worth. And then R is just some rate of decay. It's not your decay factor, it's your percent rate of decrease. And we do write that percent as a decimal again. So just watch out for that. So as a little for instance, somebody buys a television for $1,200. Must be a big TV. And then they're asked to sort of do a couple of things with this $1,200 TV. It's going to decrease by 21% each year. We're supposed to write an exponential decay equation to represent the value of the television after t years goes by. We're supposed to use our equation to estimate how much that TV is then worth after 2 years, and then graph the model. And we're going to use that graph to estimate, when is my TV worth only $300? How many years? If you're somebody who likes to sell things on Craigslist, this kind of problem might be up your alley. Guess how much your stuff is worth. So you'll see here that I set up my decay equation. I have y equals 1,200 because that was my initial amount. 1 minus 0.21 raise it to the t power. I had to simplify it, and then I had to let t equal 2. Notice there's no words like compoundings or anything like that, so we're not using the formula that we talked about at the beginning of today's lesson. And then I graphed the equation, threw it into my calculator, adjusted the window a little bit. So if you let t equal 2, you end up getting y is about $748.92. Not bad, still more than half. But it is only 2 years, I guess, so hope it'd be worth a little more than that, huh? And then they said, hey, you know, when is this thing going to be worth only $300? So $300, that's like right in between 2 and 4, right? So like right in here somewhere. Should drop down a little lower. I think I missed again. But I traced it out on my calculator. I got about almost 6 years. You can go to your table, figure out when your y value is about $300. But again, eyes on the prize. Our goal in this chapter is to solve for that variable exponent. We'll start doing that with logarithms at the end of the week. You have 7-2, practice B for homework tonight. You also want to finish up the notes. So any blanks that there are, you want to take some time to fill those in. Oh.